starting with this lecture, we're going to switch gears a bit. And up to this point, we've been taking a look at substances that we would consider solids and asking what happens to them. But now we're going to start taking a look at other states of matter. In particular, we are going to be looking at fluids. And by fluids, I don't just mean liquids. Technically, I mean liquids and gases. On the screen, what you see are representations of some of the different states of matter that exist in the universe. Those three in the middle, solid, liquid, and gas, are the ones with which you're most familiar. You can imagine a solid, you raise the temperature, it melts into a liquid. You imagine a liquid, you raise the temperature, it boils into a gas. What happens if you were to keep heating up the gas and you would start stripping the electrons off of it, and you would create a mixture of positively charged ions and negatively charged electrons that act very much like a fluid, and we call that a plasma. Some more exotic states of matter. There's the superfluid, which exists for a small number of substances at extremely cold temperatures. And then there's degenerate matter, which is basically what happens if you take matter and squeeze it under unimaginably enormous pressures. Now, I'm only going to stick to the states of matter that we commonly find here on the surface of the Earth, solids, liquids, and gases. But frankly, liquids are somewhat of an unusual state if you look at the universe as a whole. You'll find solids, you'll find gases, you'll find plasmas, and you'll find degenerate matter. You're not going to find too much superfluid or liquid. But we live on the Earth, solids, liquids, and gases. As I said, the states of matter that we call gas and liquid are both types of fluids. Why are they called fluids? Because both gases and liquids will change the shape of their volume in order to accommodate the portion of space in which they exist. If I pour them into a round sphere, then these shapes are going to adopt a round configuration. That's not the same with a solid. If I take a brick and I drop it into a liquid container, what I have is a brick. It's a rectangular solid. But if I take a liquid in one container and I pour it into a differently shaped container, the liquid adapts to the shape of that new container. And the gas is very similar. Those substances that behave that way are called fluids. Superfluids and plasmas are also fluids, but we're only going to look at liquids and gases in this course. An essential topic in the study of fluids is pressure. Undoubtedly a word you've heard of before, but we're going to quantify it. We're going to give the physics definition of it. Pressure is force over area. Greater force, greater pressure, but if you concentrate that force into a smaller area, then the area experiencing that force experiences a higher pressure. It's like the difference between having somebody step on you while wearing a sneaker and having somebody step on you while wearing a stiletto high heel. The sneaker, it sucks, but it's not going to cut into you or anything, but that stiletto high heel with all the weight of that person in that tiny area pressing up against your skin, that can puncture you. That can cause some serious damage. To account for this definition, we have an equation. Pressure, which is regrettably represented by a capital P, not to be confused with power. Pressure is equal to force divided by area. So pressure is proportional to force. As force goes up, pressure goes up. But pressure is inversely proportional to the area that experiences the force. So if that area goes up, if the force is spread out over a greater area, then the pressure goes down. The atmosphere exerts a pressure on you. It exerts a pressure on you because the atmosphere is made up of a gas, and the gas is a fluid. And you have a lot of gas above you. We call it the atmosphere. Turns out that the gravitational effect on the atmosphere is such that the force, the gravitational force, averages out to 101,325 newtons per square meter. So imagine a square meter on the ground and all of the fluid above it, all of the gas above it, the atmosphere above it is exerting a weight equal to over 100,000 newtons. It's exerting a weight that is equivalent to 10,340 kilograms in that square meter. And the fact is, you experience atmospheric pressure. It is pressing on you right now. It's pressing you in all directions. There is 10,340 kilograms of weight pressing down on you per square meter right now. And considering that the average surface area of a human being is not dramatically different from a square meter, that is a lot of atmosphere acting on you. And yet we don't feel crushed. We don't feel crushed by it because this is the environment in which we evolved. If we were an organism that felt that this was a crushing pressure, well, we wouldn't have reproduced. We wouldn't have been able to survive long enough to create offspring that would also experience this as crushing pressure. So we evolved. We had an equilibrium with it. This is normal for us. If you get into a situation where the atmosphere is close to zero, then the blood pressure within you can start basically creating lots of bruises as blood vessels burst. Take a look at this example and ask yourself a question. We have two identical bricks. Brick A is just beneath the surface of the water. Brick B is at some greater depth. The force that you need to hold brick B in place, how does that compare with the force to hold brick A? Use your imagination. Think about it. Let's take a look at an example of using that expression, force over area. What is the pressure exerted by a hammer on the head of a nail when the hammer strikes it with a force of 86.3 newtons? We need to know the area of the head of the nail. And I'm going to say that's 2.61 square millimeters. That's not standard units. We need to convert square millimeters of area to standard units of square meters of area. This is perhaps a little deceptive. You might know that there are 1,000 millimeters in a meter. But if we are looking at area, we are looking at millimeters times millimeters. So what we can argue is that there are 1,000 squared millimeters squared in 1 squared meter squared. Or in other words, since 1,000 squared is 1,000,000 and 1 squared is 1, 1,000,000 square millimeters is equivalent to 1 square meter. So in standard units, the area of the head of the nail is 2.61 times 10 to the negative 6 square meters. We're now in a position to calculate that pressure, the force divided by the area. The force is given as 86.3 newtons. We just determined the area in standard units. We get that the pressure is 3.31 times 10 to the 7, and the units we have, newtons per meter squared, has been renamed the Pascal. Blaise Pascal was a French scientist who did a lot to advance our understanding of liquids. He's also a philosopher who is known for Pascal's wager. If you're interested, you might want to look that up. It doesn't have anything to do with physics, though. But another way of re-expressing the answer is that the pressure exerted by the hammer on the nail is 3.31 times 10 to the 7 pascals. Now, that might sound like a lot because atmospheric pressure is 100,000 pascals, a little over 1 times 10 to the 5 pascals. This is over 300 times greater. But let's face it, if you had a choice between having your finger in the atmosphere or having your finger in between the hammer and the nail as the hammer comes down, I think we would all choose to just have our finger in the atmosphere. Another unit of pressure that is commonly used, this is not the standard unit, Pascal is, but a commonly used unit is the atmosphere. The atmosphere is equivalent to 101,325 pascals. It's about 100,000 pascals, one atmosphere. Now, to understand pressure allows us to understand Pascal's principle. Pascal's principle is something that we get everyday use out of. We see Pascal's principle in action in the picture, in which there is a hydraulic lift, but for instance, brakes, hydraulic brakes, that sort of thing is another example of Pascal's principle in action. What is Pascal's principle? Let's take a look at a video that discusses Pascal's principle by a demonstration. The demonstration involves some water, 2 syringes, and a clear plastic hose. And what they're going to do is they're going to fill up one of the syringes, they're going to put some glue on it, and they're going to affix the one end of the clear plastic hose to that glued end. They're going to take the other syringe, they're going to use it to inject a lot of water, filling up the clear plastic tube. And once they have that clear plastic tube filled, they're going to glue the second syringe onto the first. Now they're finding out, we should probably fill up the hose a little bit more, make sure that there's water throughout the entire system. Basically, there is now a connection of water from what's in the first syringe to what's in the second syringe. And what we're going to do next is we are going to take this to basically a display board, and it's going to create a U-shape. And in between the syringes, let me pause here, in between the syringes, from this syringe on the left all the way to this syringe on the right, we have a bunch of water, a continuous volume of water. And when you press on one syringe, what you get is that the other syringe responds to it. And this is Pascal's principle in action. When you push on the syringe, the plunger of the syringe, you are exerting an excess pressure on the fluid. And that excess pressure is transmitted throughout the entire volume of the fluid. If I'm increasing the pressure on the right end by 1,000 pascals, every single piece of fluid in this connection is increasing by 1,000 pascals. The pressure throughout it increases by 1,000 pascals. So if I push down on 1,000 pascals at the top here, all along here, the pressure in the fluid has increased by 1,000 pascals, and that means that there's an additional pressure of 1,000 pascals on the opposing syringe, on the opposing plunger, and so that when you push down on one, you are going to cause the other to consequentially be pushed up, like right here. They're pushing down, and the syringe on the left, the plunger is moving up. Pascal's principle states that a change in pressure in one location in a fluid will result in a change in pressure in all parts of the fluid by exactly that same amount. It's like having a plunger and you put a weight on it to start pushing it down, and there's extra pressure on this topmost thin layer of water. That pressures the next thin layer of water. that pressures the next thin layer, that pressures the next thin layer, that pressures the next thin layer. All of the layers, all the way down, feel this excess pressure. Because it is based on pressure, we have an equation that relates our definition for pressure equal to force divided by area and Pascal's principle. Take a look at this very simplified graphic on the screen. We have two open ends of a fluid, and we increase the pressure on the side of the fluid with the small area. So we can apply a relatively modest force. If it is applied over a small area, that can result in a very large force. Very large pressure. And that very large pressure is transmitted, that extra large pressure is transmitted throughout the entire volume of the fluid. So now on the right-hand side, I have a very large pressure exerting up on this very large area. And since force is equal to pressure times area, I have a gigantic force over here on the right. A modest force on the left, thanks to Pascal's principle, can create a gigantic force on the right. So it's a way of transforming an ordinary force that doesn't require much exertion into a really large force that can really cause something to happen, like lifting a car or slowing down a speeding car. In fact, if we apply a force at one end to create a lifting force at the other end, we have our equation. The lifting force is equal to the large cross-sectional area where the lift is occurring, divided by the small cross-sectional area where we are applying that extra pressure, times the force associated with that extra pressure. If we have a very large area divided by a very small area, we can have a very large lifting force, even if the applied force is modest. So in principle, as it states at the bottom, an ant could lift the Eiffel Tower. Is this possible? Theoretically, yes. Now, what would more likely happen is the water would compress a little bit, but we're going to assume that this is an ideal fluid that can't compress at all. And so this ant pushing on this incompressible fluid is going to create a large upwards force on the right there and lift the Eiffel Tower. Is there a catch? Yes, there is, and that catch is conservation of energy. If the ant pushes down on the narrow piston a distance delta x, it applies a force over a distance delta x, that's the amount of work the ant does on the system. And that's the amount of work that goes into lifting the Eiffel Tower. So however much work the ant does on the system, that's as much work that goes into lifting the Eiffel Tower. Now, if the lifting force is absolutely that gigantic, if it's enough to overcome the gravitational force acting on the Eiffel Tower and then some, then delta x, the distance the Eiffel Tower moves, is going to be microscopically small, so small that we are not going to see any effect whatsoever. So there is a price to be paid. Can the ant lift the Eiffel Tower? In theory, yes, but the amount by which the Eiffel Tower is lifted is so small that there's no change. Let's take a look at this example. We have a container filled with oil. Now, it doesn't have to be water. The fluid does not have to be water. We can fill it with oil. Fine. And both ends are topped with a piston, and the area of the left piston is 10 square millimeters, and the area of the right piston is 10,000 square millimeters. What force must we exert on the left pin to keep the 10,000 Newton car on the right from not sinking down because of the gravitational pull acting on it? So the weight of the car on the right is 10,000 newtons. That means that there's a 10,000 newton force acting on this large area piston. What must be the force on the small area in order to prevent this plunger on the left from moving up? We want to keep things stable. What force do we need on the left? Pressure is something that changes with your depth in a fluid. Probably at some point in time you've been in a car that goes up a hill or something or whatever. You're changing altitude and your ears pop. If you've ever felt your ears pop, you've felt the effect of pressure in a fluid. In this case, the fluid is the atmosphere, which is a gas. But maybe you've done something like scuba diving, or at the very least, dove down to the bottom of a swimming pool. And you might have felt a little extra pressure on your ears when you're at the bottom of a swimming pool. Well, you're experiencing the effect of depth on pressure. When you go into a fluid, when you descend into a fluid, and the deeper you get, the more fluid there is above you. The more fluid there is above you, the more mass there is above you. And gravity is exerting a force on that mass. Gravity is trying to pull that mass down, and you are in the way. So there's a greater force acting on you the deeper you go. We're going to quantify that. We need to know the density of the fluid in question. Density equals mass over volume. We need to know the strength of the gravitational field, well, of course. And we need to know the change in vertical displacement, which I'll call delta Y. Now, what do we expect will influence pressure the deeper we go? If, for some reason, if we were 100 meters deep in one fluid, and then we were in 100 meters deep in a fluid of different density, the more dense the fluid is, the more mass there is above me. The more mass there is above me, the greater the pressure. So I would expect density, that if density increases, the pressure exerted by that fluid will increase the deeper you go. Also, the gravitational field strength. The stronger the gravitational field strength, the greater the gravitational force of the stuff above you, on you, and the greater the pressure you feel. And finally, the deeper you go. The deeper you go, the more material there is above you. The more material there is above you, the more mass there is. The more mass there is, the greater the gravitational force, and you are in the way. You experience that greater force. I'm going to say that our equation is that the change in pressure equals minus rho g delta y, where rho is the density, g is the strength of the gravitational field, delta y is the vertical component of your change in displacement. Now, why is there a minus sign? Because the deeper you go, the greater the pressure. So if you start at the surface of the ocean where y equals 0, and then you dive down, as you get deeper and deeper, delta y gets larger, but delta y is negative. Y final minus y initial. Y initial is 0 if you're starting at the surface. As you descend, y is a negative quantity. And so delta y is a negative quantity minus 0. Delta y is intrinsically a negative quantity. But the pressure is going up. So we need that minus sign up front to balance this out. Minus rho g delta y gives you the change in pressure as you descend from y initial to y final. In this equation, we assume the density of the fluid stays constant. Is this true? No. It turns out that the density of a fluid increases as you get deeper. The reason it increases is because the fluid above is pushing down on the fluid below. It's squeezing it into a smaller volume. And if the volume gets smaller, the density gets larger. This, though, is not usually a big effect for liquids. If I look at the density of seawater at the surface of the ocean, and I compare it with the density of seawater at the deepest most part, Challenger Deep, the density of water hasn't changed by more than 4%. Now that's over about 10,000 meters of depth. So it's not going to change by a whole lot over even a few hundred meters. So we would say that the density of the fluid stays constant. That's generally a safe bet when you're talking about liquids. Not a safe bet when you're talking about gases, though. Another important thing to keep in mind is that delta P equals minus rho G delta Y is great as long as you are in the same fluid the entire time. If you switch from one fluid to another, then things get a little weird. You have that dividing line. You would have to determine the pressure at the depth where you transition from one fluid to another fluid, and then you would have to start up minus rho G delta Y using the new rho. Using the new P initial and the new rho. If we take a look at this expression right here, this graphic right here, based on the expression that delta P equals minus rho G delta Y, it implies that depth is depth and it doesn't matter how you get there. On the screen, we see two different containers containing a fluid. And in one of them, it's a very ordinary container, like a glass of water or something. But the container on the right has a decidedly unusual shape. But in both situations, as I go from the surface to some depth represented by the dashed black line, I remain within the same fluid. I don't transition to another fluid. And because I remain within the same fluid, the depth at the dashed black line is the same, whether it's for the container on the left or the container on the right. Depth is depth. I don't care how you get there as long as you don't transition from one fluid to another fluid. And you can use delta P equals minus rho G delta Y. Now here's an example in which we do change fluids. We have a U-shaped tube. It is open to the air on both ends, but we have two different liquids within it. One of them is mercury, and the other is water. And if you look at the graphic, you can see how the mercury and the water are arranged. Water is only on one side of the U-shaped tube. So we have our mercury, and on the left side above the mercury is just the atmosphere. On the right side above the mercury is a column of water, and then above the water we have atmosphere. We can use the idea of Pascal and delta P equals minus rho G delta Y to answer the following question. If the side of the tube in which we have water, if the height of the water is 8.2 centimeters above the maximum height of the mercury on the left side, what is the height of the total column of water? So from where the water meets the mercury on the right to the top of the water exposed to the atmosphere, we're trying to find that distance, given that the distance from the top of the mercury on the left side to the top of the water on the right side, that change in height is 8.2 centimeters. So what we need to do is we need to figure out this distance that I've labeled S, this vertical distance from the difference in height between the mercury on the left side of the tube and the mercury on the right side of the tube. That height is represented by the red dashed line. So if we could find this difference in the height S, we can add it to 8.20 centimeters, and we can come up with the total height of the column of water. To be able to do this, we need to know the densities of the two substances. Mercury, represented by the dark gray, has a density of 13,700 kilograms per cubic meter. Water's density fluctuates a little bit with temperature. It's typically at or near 1,000 kilograms per cubic meter. Maybe this water is at a temperature where its density is 998 kilograms per cubic meter. So pretty close to 1,000, but not quite. If I want to solve this problem, I first got to make sure I understand where the pressures will be the same. The top of the water side and the top of the mercury side are both basically at atmospheric pressure. Yes, the atmosphere is a gas, and the deeper you get into gas, the deeper you get into a fluid, the greater the pressure goes up. But over a vertical distance of 8.2 centimeters, the change in atmospheric pressure is completely negligible. So we have atmospheric pressure at the top of the water side, and we have atmospheric pressure at the very top of the mercury side. And for all intents and purposes, those quantities are exactly equal to each other. But let's look at that idea from the previous slide that two different heights within the same fluid are at the same pressure. If I start at the red dashed line immediately underneath the water, and if I'm in mercury, I can go through the U part of the tube until I get to the red dashed line height on the other side. And at the red dashed line on the left side, I have the same pressure as the red dashed line on the right side because those points are at the same height, and I can go through the same fluid without interruption to get from one location to the other location. So where I see the red dashed line, the pressure in mercury on the right is equal to the pressure in mercury on the left at that location. So if we can figure out information about the pressures, the water and the mercury, the pressure at this depth on the left, the pressure at this depth on the right, then we can figure out S. What I do know is that the descent from atmospheric pressure to this depth in mercury is equal to the descent from atmospheric pressure at the top of the water to this point right at the level of the mercury on the right side. So the change in pressure over this little bit of distance S on the left-hand side is equal to the change in pressure over 8.20 centimeters plus S on the right side. On the left-hand side, that change in pressure is density, rho times G times that depth S. Now, I write rho subscript Hg because we're going to have two densities in this problem, one for mercury and one for water. So, got to make sure we are not confusing them. On the left-hand side, the depth at the red dashed line, the change in pressure from the top of the tube to the red dashed line is rho GS, where rho is the density of mercury. But on the right-hand side, that same analysis tells me that the change in pressure is going to be the density of water times G times 0.0820 meters plus S. And those two quantities have to be equal to each other. The change in pressure on the left has to be equal to the change in pressure on the right, as we discussed. And what that winds up giving us as we go through the math is that S is the change in displacement going from the top of the mercury column on the left to the red dashed line on the left. That change in displacement is negative 0.65 centimeters, negative 0.0065 meters. The total height of the water, well, the total change in displacement going from the top of the column of water to where it meets up with the mercury is negative 8.20 centimeters minus 0.65 centimeters. So the total height of the column of water is 8.85 centimeters. I hope that makes sense. Follow it slowly. Make sure you understand it. Let me know if there are questions at the start of class. Bye-bye.